Hello guys, welcome back, and in today's video we're going to learn about sound waves, which is chapter 13 of your IGCSE physics. Now pause the video now to see what topics we are going to cover today first. Now sound waves, okay, so sound waves are always produced by vibrating objects, which means that if we hear any sound at all, we are always hearing the vibrations of airwaves around us, okay? So for example, when a guitar is being played, so the guitar strings are going to vibrate the air molecules around it, and those vibrations will travel to our ears as sound waves, and we'll be able to listen to the music. The same concept works for loudspeakers or when you're speaking. But the key word here is that all sound waves are produced by vibrating objects. Now, this is a practical investigation to actually find out the speed of sound using echoes. So, to conduct this experiment, what you have to do is stand 100 meters away from a wooden wall. So this is going to be 100 meters. And if you have, let's say, 2 wooden blocks, you're going to start clapping them and then listen for the echo. So what will happen here is the sound waves will travel once to the wall and the echoes will come back to you. So it means that the total distance traveled by the sound waves is actually 200 meters. And what you will do is you're going to have a stopwatch on your hand and then actually record what's the time taken for the echo to get back to you. And let's say the stopwatch shows you 0.58 seconds. What we can do is use a simple formula, which is V is equals to D over T, to calculate the velocity or the speed of sound. Okay, so the total distance here is 200 meters and the time taken is 0.58 seconds, meaning that your velocity would be 344 meters per second. But to make sure that your experiment is right, you're going to have to repeat it to get more accurate results. So this is a practical investigation and similar questions are being asked in your IGCSE exam. They would often ask you to describe an experiment and you can write this following procedure and mention them, the keywords here and how you would do it. Now, reflection of sound waves. Similar to all waves, what you should know is that the sound waves can be reflected, and since they can be reflected, their angle of incidence will be equals to their angle of reflection. So it's not only light waves which behaves like this, alright? So sound waves can also behave in the similar manner as well, where your angle of incidence will be your angle of reflection. And reflection of sound waves can be used in some very useful applications as a matter of fact. Okay, so let's try to see what sonar is. Sonar actually means sound navigation and ranging. Okay, so we're trying to locate what is underneath the ship. All right, so this essentially is the same example as your wooden block and wall example, right? But let's see how we do it, okay? So sound waves will first be emitted from the ship and it's going to travel to the seabed or your sea floor. Now, some of these waves are going to reflect back to the ship, right? And then there will be equipment on the ship to detect the sound waves. So the total time it takes for the waves to travel once to the bed and once back to the ship is measured. And knowing this time, we actually can calculate what is the distance or the depth of the seabed below us. Now, for the location A, right, the total time measured was 15 seconds. The speed of sound in water is this much, so the distance between ship and seabed is how much, okay? So let's try to do this. So distance is equals to velocity into time. So your velocity is going to be 1480 meters per second, multiply with your time, which is 15 seconds. So you will get, let's see, 22200 meters. But let's try to look at this here. The total time, right, that it was measured has to be once to here and once back up. So the distance have to be multiplied by 2, so it will be 11100 meters between the seabed and the ship. Now, do the same for location B. Pause the video and do the problem for location B and see if you can actually get it right. Okay, so the distance that you should be getting is 18,500 meters. Alright, I hope you get it right. So sound waves can be applied in different places, such as detection of marine life, or in World War II, we use it to detect submarines as well. Okay, so the technology will always work the same. You're going to be emitting a wave, and if there is an object here, it will reflect back to the ship. And based on the time and based on the velocity of waves in water, you can always find out what the distance to whatever object, whether it's a fish or a submarine or the seabed is. So the concept will always be the same. Alright, so since waves, all waves can be refracted as well, right? And sound waves is just one of the waves. Sound waves can be refracted as well. Now the speed of sound is faster in hot air than cold air. It's because hot airs have molecules which are going to be moving a lot faster, meaning that the vibration of the sound waves will be transmitted much faster in the hot air. Okay, so if we have a change in speed of a wave, you should remember that the direction is always going to change as well. For example, on a very hot day, the air near the ground is going to be so hot, so the sound waves will be refracted towards the cold air. Now, in the same way, on a very cold night, the air near the ground will be very cold. Okay, so the sound waves will be refracted downwards. Why? Because of the change in speed of sound. And when we have a change in speed of a wave from one medium to the other, we will have refraction, similar to your light waves. Now, this is a practical investigation for investigating frequency of sound wave using a device called oscilloscope. So this is very simple as a matter of fact, okay? So when sound waves from a source, such as, let's say, your tuning fork or your guitar strings, enters the microphone, the microphone is going to transmit data into your oscilloscope, which we will be able to see as transverse waves, okay? And on there, we can actually see the waves amplitudes as well as frequencies. So let's do one question here, which is a very common question being asked in IGCSE. What is the period, frequency, and amplitude of this sound wave? So if we want to find out the period, you know that it is the time taken for one wavelength to complete. So it's 1, 2, 3, 4, 4 squares, right? So your period or T would be 4 into, since in the x direction, each square is 0.25 milliseconds, so 0.25. Be careful that it's milliseconds here, so 10 to the power minus 3. So you would get 10 to the power minus 3 seconds. Now, how about frequency? Okay, so before we get into frequency, let's do amplitude first. Amplitude means the maximum distance from your equilibrium line, right? It means this. So since it is 2 squares, it would be 2 multiplied with Y direction, 1 square is equals to 1 volt. So it would be 2 into 1. We would have 2 volt. Alright. And since we want to calculate frequency, the equation that we would use is V is equals to F lambda. And since it's the frequency that we want, it would be V over lambda. Now, your velocity of sound in air, let's assume it to be 340 divided by your wavelength. So your wavelength, you should know, is this one, okay? From this place to this place. So it has 4 squares as well, which is the same as your period. So you'll be dividing 340 by 10 to the power minus 3. So your answer would be 340 into 10 to the power 3 hertz. Now, pitch and frequency. Now, very small objects such as the violin or the guitar strings, right? If you can see the video here compared to the shallow below, they're going to be vibrating very quickly and it will produce very high frequency sound waves. And high frequency means that the notes will be high pitch. But for large objects such as shallow strings, the vibrations will be very slow, okay, compared to your guitar strings or your violins. Hence, it will be producing very low frequency sound waves. So low frequency means that it's a low pitch notes. Okay, so let's try to see the comparison between high pitch and low pitch notes. Okay, all right. So if I draw a line here, let's see if I can draw it here. All right. Okay, let's see. When we can get within one period, right, for low pitch, since it has a lower frequency, we can only complete one wavelength. However, for the high pitch note, we can complete at least 1.5 or 2 wavelengths within the same period of time. And that's what it means by pitch and frequency. So, audible range. So, average person can hear between 20 Hz to 20,000 Hz. So, us humans cannot hear anything lower than 20,000 Hz, and we cannot hear anything above 20,000 Hz as well. Now, if we look at this interesting diagram here, we would see that elephants will talk to each other at frequencies lower than 20, and that's why we cannot actually hear it. And similar for dolphins and bats as well. They will be communicating underwater or in the case at frequencies greater than 20,000. And that's why we cannot hear them, because our audible range is only between 20 Hz and 20,000 Hz. You should pause the video and actually see what decibel or noise intensity some of the noises around us are. But when we get older, okay, when we become grandpas and grandmas, our audible range will become narrower, okay? Not 20 to 20,000 anymore, it will be lower. And that's why we have poor hearing as we grow older. Now, loudness, okay? So loudness is directly related to amplitude, okay? So if the drum is hit really hard, high energy is being transferred to the drum through drumsticks. Now the drumstick is going to vibrate up and down, okay, with large amplitude. And this large amplitude means that it will cause very, very loud sounds. But if the drum is hit very slow, only small energy is transferred to the drum, and thus the drum skin will only vibrate up and down with very small amplitude. And this small amplitude will cause very quiet sounds or quieter sounds compared to your large amplitude. So you should know that loudness is directly related to amplitude. Now, let's try to see the difference between loudness and pitch, because loudness and pitch is not related to each other. Okay, just because something is loud doesn't mean that it has a high pitch. Now, let's draw some example here to see it, okay? So now let's draw two sound waves of different loudness, which is going to have the same pitch. So first wave, I'm going to draw this as like this. Okay, so if I want to draw a different loudness, right? What I'll have to do is, this is my amplitude, right? So I will have to decrease my amplitude, which will look like this. Now let's try to compare these two. Obviously, the second one is going to be quieter because why? It has a lower amplitude. But they are still going to have the same pitch, which means their frequency is still going to be the same. What I mean by that is that it took me 1 grid, 2 grid, 3 grid, and 4 grid to complete one wavelength, right? It is still taking me 1, 2, 3, and 4 grids for me to complete one wavelength, which means that I have the same pitch, same frequency, but I just have different loudness, which is different amplitudes. Now, for this one, try to draw on your own two sound waves, which is going to have the same loudness, but have different pitches. Okay, so I hope that your diagrams look like this, okay? So let's try to see it here. So I'm having the same loudness. Why? Because I have the same amplitude, which is exactly the same for both. But since I say that it has different pitch, meaning that my frequency is going to have to be different. So let's see, it took us 1, 2, 3, 4 grids to complete one wavelength. However, it only took us 2 grids to complete one wavelength for the second wave. So again, our loudness and pitch is not related to each other. Loudness will only depend on our amplitude, while our pitch is going to be dependent on frequency only. I hope that you are not confused on this anymore. Now, as for the last discussion, what I want to mention here is that sound waves are able to travel through solids, liquids, and all gases because we've got particles inside solid, liquid, and gases which will act as messengers who can carry over these vibrations, okay? So for example, we are able to hear someone talking in the next room because the walls have solid particles which will carry the vibration. And similarly, underwater, right, in the sea, dolphins can actually communicate with each other because the liquid water particles can carry vibration. And the reason why humans are able to talk in air right now is because all the gas or the air particles carry vibrations when we talk. Now, among the solid, liquid, and gases, sound waves will travel fastest in solids because there are so many messengers here. These particles will act as messengers. Let's say, right, for solids, we're going to have like 15 to 20 messengers. For liquid, we'll have, let's say, around 7 to 8 messengers. For gases, we have around 3. So it means that if we have more messengers, more particles, we can the sound waves will be delivered faster. Okay, so that's how the concept works. But for vacuum, we cannot hear sound in space or vacuum because there are no particles, okay? There are no messengers to carry our vibrations as sound waves. So that is all for the sound waves lesson. I'll make another video, make sure to check that out, which is going to be involving common questions being asked in IGCSE about sound waves. That's all for today, and I'll see you guys next time. Bye bye.